Hello everyone and welcome to this lecture in which we will continue our journey and consider the properties of pure substances. In the last class, we had considered a hypothetical experiment in which we had a piston cylinder arrangement and we had loaded the piston with some fixed weight. So, the fixed weight plus the weight of the piston led to some pressure acting on the inside volume. So, this is the case of a isobaric system. The pressure acting on the system was kept fixed and then we applied some amount of heat from the bottom, as a result of which when we went from liquid, which is 0.1, when we heated the liquid, we went from 0.1 to 0.2 up until all the liquid got converted. So, up until the first vapor started forming. So, at 0.2 vapor just starts to form, the liquid starts to boil, and we know once a liquid starts to boil, it absorbs whatever heat you are supplying as a latent heat. So, temperature does not rise. So, given the fixed pressure, despite the change in volume, despite there being a change in property, the temperature does not change. So, through the region 2 to 3, the temperature remains fixed, and then once all the liquid is converted to vapor, there is now then again a rise in the temperature. So, inside the zone between the points 2 and 3, that zone is called as the saturated region. In that region, we have a mixture of liquid and vapor, where 0.2 is purely liquid, but 0.3 is purely vapor. So, despite there being a difference in the volumes, the temperature and pressure are fixed. So, we cannot independently vary temperature and pressure in this region. Outside that, yes, but inside this zone we cannot do an independent variation. So, we had seen that inside the region the quality x was a very important parameter. So, x was defined as the mass of vapor by total mass. So, x equal to 0 implied pure liquid at saturation, x equal to 1 implies pure vapor at saturation. The temperature is known as the saturation temperature, and the corresponding pressure that we have applied is called as the saturation pressure. So, corresponding to this saturation pressure, we have this saturation temperature. The meaning of saturation in this case refers to boiling, because liquid is going from liquid state to vapor state. So, now we had also seen that if you increase the pressure, then the saturation temperature also increases. There is nothing but stating the fact that as the pressure applied increases, the temperature at which the liquid boils increases. So, for example, we have a pressure cooker, we increase the pressure. So, things start boiling at a higher temperature. This is what we infer. So, now similar to this liquid vapor transition, we had seen that at a certain pressure there is no two phase region. There is a point of inflection over here, and then the liquid simply goes to vapor. There is no two phase zone. So, this point is called as the critical point. We had also noted at the critical point, anything below the critical point, only then liquid can exist. So, for pressures below the critical pressure, only then can there be a liquid. Any pressure higher than the critical pressure, there is no liquid, it is just some continuum business going on, where liquid and vapor are just some phase, and there is no liquid what we identify as a liquid, it is just a fluid phase. So, that is why in order to liquefy helium or in order to liquefy hydrogen and all this, one has a tremendous challenge. One has to first increase the pressure to such an extent that you can actually go, you have to reduce the pressure to such an extent that you can actually liquefy something. Okay. And ordinary pressures are so large that you cannot liquefy helium and hydrogen, no matter how much you work on it. Okay. Thus, you have to go below that critical point in order for the liquid to exist. Okay. So, with these ideas, let us see. So, this kind of diagram we can clearly identify the phases. There is a liquid phase, there is a vapor phase, and in going from a liquid phase to vapor phase, we have a two phase. Similar to this, we can draw this kind of a phase diagram. So, this is a pressure versus temperature plot. What we had drawn was a temperature versus volume plot, where we had seen that the volume kept on increasing during the heating of the two phase region and the temperature was fixed. But we can obtain some more information if we look at the pressure temperature plot. We do not refer to the volume in this plot. So, in this phase diagram, if we start off at a pressure and temperature over here, and given a fixed pressure, if you increase the temperature, we go from a solid phase to a vapor phase, and that process is known as sublimation. A very famous example of sublimation that occurs at room temperature is that of camphor. If you keep camphor in the open, it's said to sublime. Okay. So, if you keep on increasing the pressure, suppose we work in this region, we have a relatively higher pressure. At a relatively higher pressure, the molecules are acted upon by a larger force, a larger tendency to compress them. The larger the tendency to compress molecules, the larger the tendency for them to remain as a solid or a liquid. Because the pressure here was low, so at low pressure and low temperature, you do have a solid, but at that low pressure, the moment you start increasing the temperature, the molecules have enough energy to quickly go into vapor state. They do not transit into a liquid state. However, when the pressure is large, then instead of directly going into a vapor state, the liquid goes in, the solid first melts. It undergoes a transition from solid to liquid and it crosses something called as a fusion line. Okay. So, it goes from solid to liquid. So, the molecules have enough energy because of the increased temperature. I have increased the temperature by keeping the pressure constant. So, essentially the solid molecules have now a larger amount of motion and thus they go into a liquid phase. The larger pressure makes them not go into a gas phase directly. But now over here, if I still keep heating it, that is to say I keep increasing the temperature, then suddenly at a point which is called as the vaporization point, it goes into a vapor stage. Okay. The volume axis is actually orthogonal to this page. What you see here is the pressure temperature. We will see in the next plot that the volume is orthogonal to this and there is a distinct change in volume as we do the process. Okay. So, this point is called as a vaporization line. So, this process is the standard process that we observe at atmospheric conditions for water. We have ice which we then heat, it transits into a liquid which becomes water which then transits into vapor. At a certain pressure which is corresponding to this, and as we increase the temperature, there comes a point where there is no distinction between the liquid phase and the vapor phase. This point we have already seen in the temperature volume diagram to be the critical point. So, beyond that pressure, there is no existence of a fluid, of a liquid gas interface. It is simply a fluid. Okay. It is simply a fluid interface. So, what happens at an intermediate pressure between this pressure where there was sublimation and the higher pressure where there was a gradual transition? There occurs a point where the solid, the vapor and the liquid are in equilibrium. So, at this particular point, we have an intersection of the three phases. Along this particular line, for example, along that particular line we have an equilibrium of solid and vapor. along this particular line we have an equilibrium of liquid and vapor, along this particular line we have an equilibrium of solid and vapor. But all these phases are intersecting at this particular point, which I mark as pink, and that point is known as the triple point. It is the pressure and temperature at which all the three phases can coexist. So, this is very important in various kinds of applications in physics. In typical thermodynamics usages, we will bother mostly about liquids and vapors, because in typical processing plants and all this, that is what we encounter. However, in newer technologies such as adsorption and all these things, one does need to have some kind of information about the solid, liquid and all these things also. But we will mostly focus on the liquid and vapor phases. Let us see how these plots look in 3 dimensions. So, what we have just seen was, so to say, a projection of the pressure and temperature. So, if I view this 3-dimensional surface from this particular side, I will disregard the variations in volume and I will simply observe a pressure versus temperature plot. This is what we have just seen above. So, if I start off at this point, for example, okay, which is in the vapor zone, I keep increasing the pressure. So, if I move along this particular line, it simply means I am keeping the temperature to be fixed. So, along this line temperature is fixed because it is a line of constant T. It is parallel, it is orthogonal to the temperature axis. So, it means along these lines you keep temperature constant. So, now if you keep the temperature constant and essentially increase the pressure, the point, because it is quantified by two properties. See, yesterday we have already seen that we need two independent properties to define the state. In this particular case, the temperature is fixed, so temperature becomes one property, and in this region we can vary the pressure. If the pressure is increased, it starts moving along this particular thermodynamic surface. This surface is called as a thermodynamic surface. So, the moment we reach point B, the vapor has reached the saturation point. Now, we have already seen that now pressure and temperature cannot be independently varying, and thus from point B to point C, because the temperature is fixed, the pressure is also fixed, because B to C is two phase, it is saturated. So, from B to C, it is a straight line which is orthogonal to the pressure axis. So, this line has constant pressure, it corresponds to this particular line if I look in the pressure versus volume plot. So, pressure versus volume plot is simply this thermodynamic surface viewed from the front. So, here the pressure remains constant. Now, as pressure keeps on increasing, we suddenly transit from this solid vapor zone, this two phase zone, into a solid zone. Okay. All this is happening because we are working in a temperature zone which is below the triple point, and the moment we are below the triple point, there is an equilibrium of solid and vapor. This is not the case of a liquid and vapor. So, thus we have vapor over here, solid plus vapor over here, and then solid over here. This is what happens. The moment we go above the triple point, for example, this particular line, we have a transition of vapor to liquid plus vapor, wherein from point H to point I, the pressure will now remain constant, after which there will be a transition to liquid. So, it corresponds to this particular plot. Okay. So, you have kept the temperature constant, now you are increasing the pressure, T constant, P increasing. So, during the two phase zone, the P does not change, only the volume is changing. Thus, pressure and temperature are locked in the two phase zone, they cannot be independently varied, only the volume varies, and thus the quality becomes the only parameter which can help us in this region. The independent property can be temperature and quality, T and X, or it can be P and X inside, or it can be P and V also. We have already seen how to calculate the specific volume by using the quality. For that, we just need to know the specific volume of the liquid, specific volume of the two phases rather. Okay. All this can be used. So, this particular diagram is the thermodynamic surface for a surface in which liquid expands on freezing. Okay, that is the case for water. Water is a bit of an anomalous entity. So, liquid expands on freezing. That is why this slope is negative. So, it means that as the pressure increases, the temperature at which the solid liquid transition occurs decreases. But in typical other kinds of fluids, other solvents like ethanol and all these things, other refrigerants, as the pressure increases, the temperature at which the solid melts increases. Okay. This is the only case where the reverse happens. This is the case for water. As the pressure increases, the temperature of melting of ice decreases, but for other fluids, as the temperature increases or as the pressure increases, the temperature of melting increases. So, one can similarly look in this particular diagram that below this triple point, you have the solid vapor equilibrium. So, if you have an isothermal process where you are increasing the pressure, you go from vapor to solid plus vapor and then to solid, whereas if you go above the triple point, okay. So, in this diagram obviously it is not a point, it is a triple line, because that pressure is always a line in this two phase zone. So, above the triple line there is vapor, as the pressure is increasing it then transits into a two phase region and then it goes into a vapor, it then goes into a liquid zone. So, this is the liquid zone. Okay. So, it is not very difficult to understand, but all you have to understand is whether your operating temperature is below the triple point when you are starting, or your operating temperature is above the triple point when it is starting. Below the triple point, you do not have a liquid vapor or a liquid solid equilibrium, all you have is a solid vapor equilibrium. Above the triple point, you can have both the kinds of equilibrium occurring, which is solid liquid and liquid gas. Okay. All these things are much more clear if we do more examples, which will be done in the later classes. So, let us move on to something which we may require later on, which is ideal gas relationships. So, we know from our preliminary knowledge that we have picked up in class 11 and all these things, that PV is equal to N RT. So, let us call it as R bar, it is a molar thing. So, any molar quantity we represent as R bar, where R bar is now the universal gas constant. This is 8.314 kilojoule per kilomole Kelvin. So, given pressure and volume, and if you know the number of moles, you can then ascertain what the temperature is. So, given two quantities, you can find out the other quantity. So, we can write it in terms of our specific quantities that we have learned, because we know that the number of moles is the weight taken of the gas or the substance by its molecular weight. So, then we have pressure into volume, total volume is equal to weight taken by molecular weight into R bar into T. We take the weight taken to the left hand side, P into volume by the weight taken is equal to R bar by capital M times T. Now, we have already seen that the specific volume is nothing but the total volume or the total mass. In this case, if we use the symbols, which is V by W, and therefore, this implies that P into small v, the specific volume, is equal to R into T, where R is now the gas specific universal constant, which is the universal gas constant by the molecular weight of the gas. Okay. And thus, we have the relationship P V is equal to R T. Now, this holds true for ideal gases. When is a gas ideal? A gas is ideal when, see, what are the basis or what was the basis of the assumption behind the ideal gas? When the pressure is very large and the temperature is very low, the molecules have a very strong attraction amongst them. When the pressure keeps on increasing, we have already seen that the molecules tend to collide more and they tend to form a liquid more. So, when the pressures are small, the molecules are almost not interacting with each other. Okay, there are less collisions going on across molecules. So, each molecule is encountering some other molecule, but they do not have a tendency to coalesce together. And when the temperature is large, when they have large amount of energy, so that they are not bogged down by any potential. See, every molecule has some potential which tries to absorb other molecules and so on. So, if the temperature is very large and the pressure is very low, the molecules are behaving like ideal particles and they are colliding around without really interacting with other molecules. They are just colliding with a wall. That gives us the notion of a pressure. So, for low pressure and high temperature, we go into the zone where the gas behaves like an ideal gas. But a more fundamental measure of the deviation from ideality may be defined by means of the compressibility, defined as this. So, when Z equal to 1, the gas is said to be ideal. If Z is less than 1 or greater than 1, then the gas shows deviations from the ideal gas behavior. So, this kind of things are then accounted for. So, we have read this in the past that there was the van der Waal correction, which is the excluded volume and the additional pressure and all these things. But I mean, those are not a part of this course, but one should have an idea that this kind of corrections do exist and there are virial coefficients which can account for the deviation from the ideal gas equation. But in this course, when we will do air standard cycles and all, we will make use of the ideal gas, because usually turbines and all are operating at a very high temperature where this ideal gas may be valid. So, in this kind of diagrams, so pressure versus volume. So, in these regions, these are sort of the zones where the ideal gas equation may be assumed to be valid, without incurring a very strong error on the work done and all these things. See, ideal gas is a very strong idealization. There will never be an ideal gas, but as long as it gives you less errors, you can make do with it, because it simplifies life. It gives you a very good relationship, a very clean relationship to find out one of the independent properties if the other two are known. So, if pressure and volume are known, you find the temperature, the pressure and temperature are known, you can find the volume. Okay. So, ideal gas relationships gives a very nice and easy way of finding out the other property. So, with this we wrap up properties of pure substances. In the next class, we will see a few examples on how to use the computerized tables, because one needs to know how to look up the various properties, when to know if the property is a superheated vapor, when to know the properties, how to find the properties when the fluid is a super cooled liquid, how to find the properties when it's in saturated region. So, in the saturated region, you can only specify one of the properties, temperature or pressure. You cannot satisfy both temperature and pressure. So, then you need to have the quality. Okay. So, all these things will first be discussed by means of the tables given in the book. It can be found in any appendix in thermodynamics books, and there are entire tables dedicated to this. They are known as steam tables. Okay. And then we will see how to make use of computer aided tables in order to solve such kinds of problems. So, there is no interference between looking up the value in a table and using a computer to fetch that data. If the concept is there, you can very well make use of computer to fetch the value of the property that you need, and then you can do the calculation. Okay. So, we will first see how to find out how to extract the particular values. We will see how the critical temperature can be obtained, how we can find all these things. So, I will see you next time. Thanks.